Okay, hello everyone. So we're going to continue. Today we're going to start talking about transversality, which is the first main topic of the course. And we will start, let me say this is number 1. And the first subtopic that we're going to cover today is Sard's theorem. Okay, so this is a theorem that you might have seen already for functions in the Euclidean space, but I'm going to state it in generality for manifolds. But I mean, the proof, as you'll see, is very local. So it is really just a theorem about our functions from Rn to Rm. But before, I have to remind you what it means for a set to have measure 0. If you've taken a course on measure theory, you probably know this already and you're very familiar with it. But maybe some of you have not yet. So let me remind you what it means for a set to have measure 0. Let's just write it like this. If I have two vectors, A and B, all positive, so this is an Rn greater than 0, I can define what's called a cube, or to be more precise, it should be a parallelogram or higher dimensions. But this is just going to be the product of the interval A1, A1, B1 times, etc., times AN, BN. So this is inside of Rn. So okay, so A1, B1, A2, B2, A3, B3, or something like that. Well, to be consistent with their usual, this is usually X, Y, and Z, so let's just be consistent. This will be A1, E1, A2, B2. All right. Okay. So for such a cube, we define the volume of the cube as just the product of the differences. So this is very standard. So the product of AI, of BI minus AI. Okay, so now I can say what it means for a set to have measure 0. So a set in Rn has measure 0 if for every epsilon greater than 0, there exists a sequence of open cubes such that S is contained in the union of the cubes, and the sum of the volume of the cubes is less than epsilon. Okay, so if I can, if S is covered by a union of open, here I'm just considering open cubes, doesn't matter if they're closed, whose total volume is as small as you want. Okay, so that's what it means to have measure 0. And of course, I think most of you have studied measure theory before and know that you can actually talk about measures of a lot of sets in Rn, and measures that are not 0. But I'm not going to talk about that. It's completely unnecessary. But what I can tell you is, well, before that, let's just have to look at some properties of measure 0 sets. So proposition. Well, number 1, if S1 is contained in S2, and S2 has measure 0, then S1 has measure 0. So that's pretty much straightforward, but let's state that anyways. Number 2, yeah. A countable union of sets of measure 0 in Rn has measure 0. And the third property that we're going to use is that if I have a function from Rn to Rn, it has to be the same n, well, to start, and then S, and it's a C1 function, and S has measure 0. Then its image, f of S, also has measure 0. And the fourth property that I'm going to state is that an open set, a non-empty open set, does not have measure 0. Okay. In particular, Rn does not have measure 0. Okay. In particular, Rn does not have measure 0. Okay. So let's prove this. I mean, this is a very kind of well-known. These facts are all very well-known. So let me just kind of sketch some of the results. Yeah, I think I won't even prove number 4. So let's see. I think number 1, I don't even have to write anything down. I think number 1 is pretty much obvious. That if you have a covering for S2, then it's also a covering for S1. So number 1 is obvious, but I think it's worth stating. Number 2. Okay, so number 2, let's write down. It's kind of a nice little exercise in analysis. But so if you have a countable union of sets, so let's say that I have a collection Si of sets of measure 0. And you always have to fix the dimension of the space that you're in. So these are sets in Rn. Okay. So let's see that the union, so the claim is that the union has measure 0. So how do you prove that? So first you fix an epsilon, and you have to show that there is a covering for this, which has measure, there's a countable covering that has a total volume less than epsilon. So we fix an epsilon. And now since we can find an open covering for each one of the SIs for every epsilon, then what you do is now you take a covering Cij, where j goes from 1 to infinity. So you fix the I, and you let j vary. This is going to be a covering for an open covering for Si by open cubes, such that the total volume of Cij, for j equals 1 to infinity, is less. You can be less than or equal to whatever number you choose. So you pick epsilon over 2 to the j. Very standard technique. So then now, so you do that for every j. So now clearly, if you take Cij, varying both I and j, this will be an open covering, of the union of the SIs by open cubes. Okay? And then now, what's the total volume? So what is, and of course, this is countable. So you can, if you want, you can reorder that into just one index. But I'm not going to do that. I think everybody's familiar with that. So the sum of the volume of this guy, Ij, from I and j going from 1 to infinity, you can, this converges because you can rewrite this as the sum over j. Yeah, the sum, oh, sorry, this is I. Yeah, so I'm summing over j, and this is epsilon over 2 to the I for every I. Okay, so this is the sum over I of the sum over j of this volume, which is the sum over I of epsilon over 2 to the I. And this is equal to epsilon. Okay. So this is very simple and very standard, but it's a nice little exercise to do here. Okay? Any questions about this? Yeah. Oh, thank you. All right. So that's number 2. Number 3, that's a little more interesting. So if I take a set of measure 0, then its image also has measure 0. So how do we show that? So first, we can cover Rn by a countable number, a countable union of compact sets. So you might as well assume that S is already contained in a compact set. Because if it's not contained in a compact set, so you can cover it with a countable union of them. So you can show that for each of these compact sets, the image of S intersected with this compact has measure 0. Well, let me write what the implication would be. So basically, if F intersected the compact, if this guy has measure 0, and you can show that this guy has measure 0 for a compact set, then by property 2, this implies that f of s has measure 0. Because f of s is clearly the union, the countable union of sets of this form. Okay? So because of that, so we assume that S is contained in a compact set. Okay, so let's make it pretty again. So if it's contained in a compact set, then, and the function is C1, then we can write f of x minus f of y, the norm in L infinity. So that's the sup norm of all the variables. I think everybody knows what this means. the L infinity norm, it just means to take the, well, let me just write this down. This is, maybe not everybody knows, if x1 through xa is a point in Rn, then the L infinity norm is just the max of the absolute value of xi. Okay, so then this is less than or equal to a constant times the norm of x minus y L infinity. Okay, so this is a version of the mean value inequality in Rn. And it can do it for any norm, in particular for the norm L infinity. So now we fix an epsilon, as usual. So let epsilon be a positive number. Then we can, so then we have a open cover. So this is a covering. Since S has measure 0, we can find an open covering of S by open cubes, such that the total volume is less than or equal to epsilon over c to the n, where c is that constant. And now, because of this inequality, what happens when you take f of each ci? So ci is a cube, and what happens is that the length of the sides of the cube gets multiplied by c at most. So f of ci is contained in a cube, which is an open cube, whose sides are at most c times the sides of ci. So each side gets multiplied by at most c, which means that the volume gets multiplied by at most c to the n. So the volume of f of c, I mean, I could spell out the sides and say, this has sides a1 through an, but I don't want to overcharge the notation. I think that it's easier to just kind of say it. But if you don't understand, I can repeat. Okay, so the volume of each f of ci, this is less than or equal to the volume of ci tilde, which is less than or equal to c to the n times the volume of ci. And now we just put it together. So now the sum of the volumes of f of ci. Actually, all you want really, this part here doesn't matter. All you want is this. So now you use ci tilde to cover the image. So f of s is now contained in the union of f of ci, which is contained in the union of ci tilde. Yeah, in principle, I couldn't have written what I wrote because you don't know that f of ci is a cube. So its volume is not well defined by what I've said before. But we know that f of s is contained in the union of the f of ci, which is contained in the union of these cubes. So now, and the sum of these volumes from I equals 1 to infinity, this is going to be less than Cn times epsilon over Cn, which is epsilon. So again, this is number 3. We prove that the image of a set of measure 0 by a function that's C1 has measure 0. Okay? Any questions about this? No. And then number 4, I'm just going to leave as an exercise. It's pretty standard. It's kind of nice to kind of show that you can't really squeeze if you have like an open ball. You can't. You have the volume at least. If you can put a cube in it, then you can't have, the volume has to be at least that cube, no matter which open covering. So for number 4, I'm going to just leave it as an exercise. And just say that basically you can prove that a cube cannot have, an open cube cannot have measure 0. Because no matter which covering you have of the open cube, then you have to have volume at least that. So it's kind of like, so if you have, the exercise is, if C is an open cube, let's write it like this. C of AB, where all the guys, they're all different. So AI is strictly smaller than BI for all I. Then if CI is a covering of CAB by open cubes, then, no, let's write it like this. If this is da-da-da, and this is an open covering, then the total volume of these guys is bigger than or equal to the volume of CAB, which is bigger than 0. Okay, so this cannot be as small as you want. Okay, so this is a nice little exercise. Okay. Any questions about this? This is kind of beginning introductory measure theory, but I think it's good to be on the same page. All right, so now let's talk about manifolds. So what does it mean for a subset of a manifold to be to have measure 0? We will need number 3 for that to make sense. So now let X be a manifold. And as I said last time, every time I say a manifold, I mean a smooth manifold. So let X be a manifold. This is a class on differential topology. So I will always assume differentiability, unless I say otherwise. So let X be a manifold and S be an open set of X. We say that S has measure 0. And sometimes I'll write it like this. Mu of S is equals 0. If there exists an open covering, a countable open covering, let me write it like this. Si, I equals 1 to infinity of S, such that Si is contained in a chart, in the domain of a chart. Let me say it with words first. So if you can cover S with subsets which are contained in the domain of a chart, and then we look at the image in Rn, that has measure 0. So if S is contained in a countable union of sets, such that Si is contained in Ui, which is the domain of a chart. And there exists a chart like this for all I. I mean, you can always, so far you can do that for any subset. You can do that for all of X because the manifold is second countable. But the property is that, well, I guess I can write it like here. And phi I of Si has measure 0. Okay. All right? Great. Let me write it this bigger. Okay, so that's what it means for a set in a manifold to have measure 0. Okay, so you can see that this definition makes sense because of property 3 from the previous proposition. Because if you change the chart, you're going to change, if you change the chart, you're going to change this set by a diffeomorphism. So you apply a smooth function to this. So if it's measure 0 for one chart, then it's going to be measure 0 for any chart. Well, that's necessary for the definition to be consistent. Okay? Or that's sufficient for the definition to be consistent, to be more precise. Okay, so corollary of this, I mean, I guess this is corollary of the previous proposition, is that, so if I take two manifolds of the same dimension, so X and Y and these are manifolds, and you take a smooth function from X, Y, so if you take a subset of X, which has measure 0, then the image of S has measure 0. Okay, so this is the same as number 3, but for smooth manifolds. I mean, you really only need it to be C1, but as I told you, I'm not going to use these subtleties very much in this class. I'm just going to do everything for smooth functions. So if you have a smooth map between two manifolds of the same dimension, and you take a set of measure 0 in X, then its image is going to have measure 0. In the proof, I guess I don't even have to write it down, but you just, if S has measure 0, you split it up into charts, and then you also look at charts on the other side, and then you look at, like, all the maps are going to be, in charts, they're just going to be maps from Rn to Rn, smooth maps that will be, that will have that property. The image is going to be 0, and you can, if the sets are too big to fit in the chart, you can always make them to take a countable union of open sets so that they are small enough to fit in the chart, so that you can really look at the map F as being a map from Rn to Rn. Okay? I think this should be like a corollary that doesn't need a written down proof. But if you have any questions, please ask, and I can write down more stuff. Okay. So now there's a more interesting proposition that does require proof, so the goal now is to actually talk about functions that go from one manifold to another of not necessarily the same dimension. So before stating like Sard's theorem, which we'll talk about that, let's just do an easy proposition. So let's suppose that Y is let Y be a manifold of dimension n, and X be a submanifold such that the dimension is strictly less than n. Okay, so a submanifold of codimension at least 1, then X has measure 0. And I should say one more time that when you talk about measure 0, it's always with respect to something. So if you just take a manifold itself, if it's non-empty, it doesn't have measure 0 with respect to itself, because it contains an open set. But when I say that X has measure 0, it has measure 0 in Y. Okay? Which has this definition here. Okay? So what's the proof? Well, really, the thing that you need to show here is that Rm has measure 0 inside of Rn. So Rm, looking as a if you look at Rm as a vector subspace of Rn, this has measure 0, provided, of course, that m is strictly less than n. That's what you need to show. So let's say this is the claim. And how do you prove that? Well, it's pretty straightforward, but let me write down anyway. So first of all, you can cover our M with a countable union, with a countable collection of cubes. So you can cover Rm with countably many cubes, compact cubes. So I don't know, of length, say B. Okay, so here's a cube where the lengths are, where the sides are all length B in Rm. So let's take such a cube. Let me call this cube C. And what you can do is you can now multiply C by minus epsilon to the n minus m. Okay, so you can fill up the other coordinates like this. So now you have a cube in Rn. So this is a cube in Rn. And you can fill this with countably many cubes. So this will be a countable collection of cubes in Rn that cover Rm. And the volumes of these cubes are very small. There is some fixed volume, b to the, so that the volume of this is going to be b to the m times, I guess, 2 epsilon to the n minus m. And this can be as small as you want. Okay. And again, if you want, you can maybe play a trick where you put bi and you make these guys as a 2 to do something. And I'm not going to write down the details to get a beautiful epsilon at the end, but I think that's something you should be able to do this time. Okay? So the idea is that if you're thinking about the volume in Rn and you just take a subspace of positive codimension, you can put a cube there, you can multiply by something really, really thin, and the volume is going to be very, very small. Okay? So Rm has measure 0 inside of Rn. And this is a local model for a chart for a submanifold. So again, by the standard argument, you can cover X by a countable number of subsets. And such that when you look at charts, the image of the submanifold is the image of the Euclidean space of a vector subspace inside of the bigger space. So that's actually the end of the proof of the proposition. Any questions about this? No. You have a question? No. You have a question? Oh, okay. All right. Believe it or not, this is enough to prove Sard's theorem in one case, but it's one of the most useful cases, which I'm going to call the mini Sard theorem. So corollary of that is what's called mini Sard. And it says, let x and y, x be an n-dimensional manifold, and y be an m-dimensional manifold. Did I switch n with m? I did, so let's not confuse you. M and N manifolds with M less than N, and consider a function f from x to y smooth. Then the image of f has measure 0. Okay, so if I have a function from one manifold into another, and if the dimension of the domain is less than the dimension of the target, then the image has measure 0. Okay? So what's the proof? The proof is very simple. You can just write a different function first like this. So f tilde, that goes from x times Rn minus m into y, given by f tilde of xa. It's kind of just an exercise in notation. Really, like the harder result is that proposition. So you just basically factor your function f by this function f prime. So now if you look at x times 0, this is a submanifold of x times r to the n minus m. And this has codimension, positive codimension. So this guy has measure 0. Right, because this is a submanifold of this. This has dimension m, and this has dimension n. Okay? And it's kind of obvious that the image of x by f is the same as the image of f tilde of x times 0. And we had proven before, maybe it's written here. Yeah, it's this corollary, that the image of a smooth function from a set of measure 0 has measure 0. So we know this guy here has measure 0. So then this guy has measure 0. So therefore, this has measure 0. So what I did here, in other words, I just factored this through a map that goes here. And then I kind of just embedded this guy into here as a submanifold of dimension n. Okay, so I just saw that the image of this guy is, this is a map, I guess. Yeah. Well, let me write it like this. Now this is an actual diffeomorphism. And then I write it like this. Here's my f. Here's my f tilde. And this is the inclusion. And this is the obvious map. Okay. All right, any questions about this? So believe it or not, this theorem, we haven't even talked about regular values. This is already a version of Sart's theorem, and it's quite useful. So this is already enough to prove the easy Whitney embedding theorem. So let's prove that before we even state the full Sart's theorem. So a corollary of this is called, this is the easy Whitney embedding theorem. which says the following thing. If X of dimension n is a compact manifold, then there is an embedding of X into R 2n plus 1, and there's an immersion of X into R to the 2n. Okay, so every compact manifold can be embedded into a finite dimensional space, but you can actually control the dimension. You can always embed it into R to the 2n plus 1. And before the proof, let me just say that there's another theorem which we're not going to prove today. And actually, I'm not going to prove at all in this course. Probably not. Maybe at the end if we are motivated enough, have enough time. But I kind of doubt it. It's called the full Whitney theorem, the Whitney embedding theorem, which says that if X to the n is a manifold, any manifold, then X embeds into R 2n. Okay, so you can actually, so two things here that are two improvements from here. First is that you don't need X to be compact. It can be any manifold. It can be, a non-compact manifold. And this thing for non-compact manifolds we'll see in this course. But what's really tricky here is to go from 2n plus 1 to 2n. And that's going to require, that requires a very non-trivial step, which is basically going from an immersion to an embedding. So you basically say, okay, you have an immersion. How do you go from an immersion to an embedding? And you have to resolve singularities. That's why it's hard. So you have to say that if you have a self-intersection, you can't perturb it away, and you have to do some kind of surgery. So that's why this is much harder. This is called the hard Whitney embedding theorem. Okay, but if we talk about this, it's going to be at the very end, but it's unlikely. Okay, but let's prove the easy Whitney embedding theorem. But before that, are there any questions or comments? Yeah. Yeah? Yes, you also have that. Yeah. But I don't remember if it has to be compact for that. You might have to be compact. I can't remember. Because, yeah, I can't remember. But at least in some cases, you can prove that you can always immerse into 2n minus 1. Yeah. OK, so let's see the proof of this corollary. I think maybe some of you have seen this before, maybe not. But this, it actually can be even left as an exercise. But it's not such an easy exercise, so let's do it. So first of all, what we need, the first step is embedding X into some Euclidean space. Okay, so that's already not extremely trivial, and that's actually the place we're going to use the fact that it's a compact manifold. So how do we embed X into a Euclidean space of possibly very high dimension? So first thing you notice is that you can always do that in a chart, in the domain of a chart, kind of by definition of the chart. Right, so but the thing about it being compact is that you can do it for a finite number of charts. So we can cover the space, with a finite number of charts. So I can, from I equals 1 to big N, this is a finite atlas of X. Okay, so you can take an atlas and you can take a finite subcovering, because X is compact, so you have a finite atlas. Such that I actually want to do something similar to last time. I actually want to be able to have an open set inside whose support is contained in UI, because I want to use bump functions. So such that there exists these VIs with VI already being a covering of X. Okay, I did something very similar last time. Okay? And the reason for that is that I want to consider these bump functions. So like in particular, well, no, I don't need to say this. It's kind of obvious. So VI is a covering of X, and I can restrict the chart into VI. And when I restrict the chart into VI, I actually get an embedding. I still get an embedding into Rn. So a chart is kind of, by definition, an embedding. It's a diffeomorphism into an open set of Rn. Okay? So now what we do is we pick bump functions psi I that go from UI to R. So what's a bump function? That just means that, so this is a function whose support is contained in UI. I mean, I guess it's kind of by definition because it's defined on UI, but I want it to be 0 outside of a compact set. So I kind of, maybe what I want to say is that the support, it has a compact, phi has compact support. And the compact support of psi I actually want psi I to be equal to 1 on VI. Okay, so that's kind of the standard thing. If this is your UI, here is your VI, and I want the function to be 1 here, and to have a compact support. So if you do that, now you can actually extend psi I to a function on all of the manifold. So that means, psi I can be extended to X in such a way that, the support of psi I is contained in UI, and psi I is equal to 1 on VI. Okay, so why do I want to do that? Because now I can multiply my chart by psi I. So now if I multiply phi I by psi I get a map from all of X into Rn. This is a map. Okay, because wherever phi I is not well defined, then psi I is 0. Okay, so this guy can be extended. I mean, in principle, it only has values in UI. The domain is UI, but you can extend it because it's 0 outside of a compact set. Okay? And of course, psi I times phi I is equal to phi I on VI. So in particular, it's an embedding. So it's an embedding on VI, restricted to VI. Okay, so now what I can do is I can put all these guys together. So now I can consider a map capital phi that goes from X into Rn to the n. And that basically is just putting all these maps together. So this is psi 1, phi 1 of X, psi n, phi n of X. And the point is, because the VIs are a covering of X, then every point has an open neighborhood which is in one of the VIs. So for one of these coordinates, you have an embedding, a local embedding. So you have to check, but it's not very hard to see that this map is an embedding. Okay? So, I mean, you can do it. You have to show it's an injection, which is very easy from this thing I just said. You have to show it's injective. And again, you can show that it's pretty easy. Okay, so I'm gonna just leave it as an exercise. Psi is an embedding. Okay. There are many things that are easier to do yourself than to try to follow someone else do it. And this is one of them. Okay, so now we show that if a compact manifold can be embedded into a very large Euclidean space. And what I want to do now is I want to reduce the dimension of this guy. Okay, so my claim is that if X embeds into our M, then X embeds into our M minus 1 if M is bigger than 2n plus 1, and X immerses into our M minus 1 if M is equal to 2n plus 1. And the idea here is very simple. So basically, if I have a manifold that's embedded into some Euclidean space, what I want to do is I want to consider a subspace, a hyperplane, and I want to project this manifold to this hyperplane. And what I'm going to show is that if the dimension of the Euclidean space is sufficiently high, then you can project this so that the image of the projection is still an embedding, or at least an immersion in this limiting case. Okay? So given a vector in Rm, I'm going to let PRA be the projection from Rm to Rm minus 1 along A. So, this is linear algebra. So if I take a vector A in Rm, this determines a projection from Rm to Rm minus 1 along A. Okay? So I don't think I need to write down the linear algebra, but if anybody doesn't know what I mean, please say. Okay. And now I'm going to define two functions. So I'm going to define G to be the function that looks at x, y, and t, and takes it to t times f of x minus f of y. And h, which is a function that goes from the tangent space into Rm, which takes x and v to the image of the f of x at v. And now I'm going to make two observations. So the first one is that if A is not in the image of G, then when I compose F with the projection, I'm still injective. And second, and I can explain these two observations, but let me write it down. If A is not in the image of H, then the projection, when I project in this direction, then I'm still in immersion. And remember that my domain is compact, so an injective immersion is an embedding. Okay? But what I need to show, whatever the dimension is, but I'd like to show that after I project, I still have an injective immersion. And sometimes I lose the injectivity, but I still have an immersion. Yes? Uh-huh. Sorry, I forgot to say that F is the map, is the embedding from R, from X to Rm. Yeah. Okay, so let's see this. I mean, it's kind of, I guess you could just draw a picture, but let me. So here is the map. If you just see X as a subset of Rm, what you could just say is that you can look at the projection restricted to X. Okay, that's another way, like to just think of F as the inclusion function. And this composition with the inclusion is just the restriction. You could do it that way too. But anyway, let's write it like this. So basically, this, what does it mean? So what you're doing here is you're looking, what's the function G? You're looking at the difference of these two guys. Oh, sorry, I forgot to project. Oh, no, that's right. That's right. Yeah, so if I take something, if I'm projecting in a direction, I can kind of draw a picture and see if you can see it. I think the first one is kind of easy to see from the picture, that if you're not injective, like going the other way, if you're not injective, then when you project along this direction, then there's going to be something on the image of G. So let me just write it like this. So for number one, suppose that this is not injective, so then I think, no, that's right. So then the projection A is equal to the projection of Y, and for some X different from Y. So that means that F of X minus F of Y is a multiple of A. Okay, because I'm projecting in the. Actually, I think what I want R star. I think that's a slight mistake here. Okay, otherwise. Actually, let's finish the proof and see if we need that. So anyway, so we have two different points such that, so you have this guy here. Yeah, for some lambda in R. Oh yeah, so since f is injective, yeah, I do need that. Since f is injective, the image of x has to be different from the image of y. So lambda has to be different from 0. So A is basically G of x, y, and lambda inverse. Yeah, that's right. OK. Actually, sorry, I'll go back, and I don't really need this. This is actually good enough, this map. OK, there we go. So that means that A is in the image of G. OK? So that's number one. And then number two is kind of similar, but for the derivative. So, so suppose that when I compose with a projection, this is not an immersion. So there exists a point in x and a vector in the tangent space to x such that when I project in the direction of A, df of x of v, I get 0. So if I'm projecting along, this is the derivative of the projection, which is the projection itself. So that means that this guy has to be a multiple of A if I'm projecting and I'm getting 0. So that means that df x of v is lambda times A. OK? But since, oh, and I'm because I'm assuming it's not an immersion, then there is a v that's not 0. So the kernel is bigger than just 0. But I know that df is an immersion. So since dfx is an immersion, lambda has to be different from 0. So A, hence, A is just dfx of lambda inverse v. Therefore, A is in the image of H. And of course, for this all to make sense, I'm taking a vector that's not 0. Otherwise, it doesn't make sense to talk about projection. OK, I should have said this when I started. Okay, maybe when I wrote it like this, it's not so obvious. But I guess if you think about the picture, what's happening is, if you want the projection to continue being injective, then you can't have two vectors, 2 points that are along the same, along that vector. Okay, so that's why to make an if and only if, you have to be a little more careful. But in this direction, it's pretty easy. And that's all we need. It's this direction. OK. I guess if you want to go back, then maybe you have to make sure, be careful with zeros. The direction that I wrote down is actually pretty straightforward. OK. Any questions about this? No? No. OK. So now we can apply Mini-Sard's theorem. So by Mini-Sard, so you see that the dimension of this guy is 2n plus 1. This is a manifold of dimension 2n plus 1. And this is a manifold of dimension 2n. So if the dimension of this is bigger than this, then the image has measure 0. And also if the dimension of this is bigger than this, then the image has measure 0. So by Mini-Sard, if m is bigger than 2n plus 1, then the image of h, of G, and the image of h, they both have measure 0. So their unions also has measure 0. And if m is equal to 2n plus 1, then just the h, the image of h has measure 0. Okay? And because of what I said before, if you have an open set, then it can't have measure 0. So most things don't have measure 0. So the complement of a measure 0 set is almost everything. So in particular, you can find something that's not in the image. So that means that if m is greater than 2n plus 1, then there exists an A which is neither in the image of G nor in the image of H. So there exists an A which doesn't belong to the image of G or the image of H. So then you can use this guy here. So therefore, this PRA composed with F is an injective immersion. And therefore, an embedding. And if, and again, if m is equal to 2n plus 1, then there exists something that's not in the image of H, so you still have an immersion. Then there exists an A, which is not in the image of H. So PRA composed with F is an immersion. Okay? So that's the proof of the easy Whitney embedding theorem. Any questions? No? Okay. So now we can move towards the full Sard's theorem. So to talk about that, we're going to talk about regular values and critical values. So let me make the definition of regular and critical values. So definition, let X n and Y m be manifolds, and consider a map which is smooth. And now I don't make any assumptions on m and n. Okay? We say that, well, A, X is a critical point if the rank of the derivative of f at the point x is not maximum. So what's the maximum rank? The maximum rank that a derivative can have is the smallest of the two dimensions. Okay, so we say that it's a critical point if the rank is less than or equal to the minimum between m and n. And let's define the set of critical points of X to be the set of points which are critical. Is a critical point. Okay. And we say that a point is regular. X is a regular point if X is not a critical point. And again, Y is a critical value. And this name regular point is not used very often. This is just kind of if it comes up at some point, but it's not something that is talked about very much, regular points. But, a critical value is the image of a critical point. So Y is a critical value if Y is in the image of the set of critical points. Okay? And here, it's a little funny because you could have a critical value be the image of a regular point. It's possible, if it's the image also of a critical point. Okay? And D, finally, I say that Y is a regular value if Y is not a critical value. Another way of saying this is Y is a regular value if the preimage of Y consists of only regular points. Okay? So that's it. And now I can state Sart's theorem. This is called Sart's theorem. And it says, take a smooth function from X to Y. Then the set of critical values has measure 0. Then F of the set of critical values has measure 0. And this implies that the set of regular values is dense in Y. So, in other words, almost every point in X in Y is a regular value. Okay? So that's what it means, what I just said. But in particular, it has some people will say this. The set of regular values is dense. Okay, that's a little weaker than just saying that the other one has measure 0. Okay. So this is the one really that says, this means that almost every point in Y is a regular value. So that's how we're going to use Sart's theorem. And it's going to come up in all the applications in the big transversality theory that will continue in the next lecture. Okay, so any questions about this before we prove Sart's theorem? Okay, so proof. So the proof is going to be induction on N. Okay, so the case N equals 0 is trivial. Because for N equals 0, the manifold, sorry, I think I'm going to get confused. Yeah, actually, let me write it like my notes. I think I switched N and M. This is kind of annoying, but sorry. Before proving, let me just write a couple of observations. The first one is that you don't need to assume that F is smooth. You could assume that Sart's theorem holds if F is only CL, where L is greater than the maximum of the dimension of X minus the dimension of Y and 0. So, if L, basically if the dimension of X is pretty big compared to Y, then they're going to need a lot of regularity. But if the dimension of X is less than or equal to the dimension of Y, which is the case that we've already covered, all you need is that F is C1. Okay, which is kind of the very first proposition that we had, that a map from Rn to Rn that was C1 had the property that a measure 0 set gets taken to a measure 0 set. So you need at least C1, but this is kind of a technicality. But if the dimension of X is very big, then you'll need more derivatives. You can see this in the proof, but I don't want to kind of be so precise there. But in general, I'm just going to assume that L is infinity. But you can be, if you really want, you could require something weaker. And the second is that if the dimension of X is less than the dimension of Y, then we've already proven it. Then Sart's theorem follows from mini Sart. Okay. Because the image, because if you're not in the image of X, then you are a regular value. And we showed that the image of F has measure 0. So to be a critical point, you have to be in the image. Okay, so that's why it follows from mini Sart. Okay, so now we can prove Sart's theorem. And as usual, for this class, you can write, you can cover X with a countable number of open sets that are all contained in a chart. So really, the theorem that we need to prove is local. So we just need to prove Sart's theorem for functions of the Euclidean space. So we just need to prove a local version. So we have a function that goes from an open set into R. I think I now switch N and M, and I'm going to keep that. Otherwise, my notes are going to I'm going to, at some point, change them. So let's be consistent with my notes. So I have a function like this. And we might as well assume that U is contained in a compact set. So we can assume U is contained in a compact set. Okay. All right, so now I'm going to apply induction. Induction on N. And as I said, the case that N equals 0 is trivial. So let's assume N is bigger than 0. And so let's apply induction. So we're going to suppose this is true, that Sart's theorem is true for functions from Rn to Rm for every m, for a given n. And then we'll show that we can go to n plus 1. Okay? So we assume Sart's theorem, or at least the local version, holds for every m for a given n, or for a given n minus 1. And we are going to show that it also holds for n. OK, so there are 3 steps. Well, let's write C, the set of critical points of F. And now I'm going to write Ci to be the set of P in U, such that all the partial derivatives of F K d alpha dx alpha, this is the multi-index notation, is equal to 0 for every multi-index between I and 0, and for k between n and 1. No, sorry, m. Yeah. OK, so my function, consists of, I can think of f as m functions from Rn to R. This is the index k. And I can look at the partial derivatives where alpha is a multi-index of size at most I. So basically, all of the partial derivatives up to order I are 0. OK, so you can write this in kind of a multi-matrix definition, notation if you want. But I think this is the easiest way to say with partial derivatives. So Ci are the set of points that are like very critical in a way. It's not only a critical point, but it's all the derivatives are 0. Okay, so now I want to show that. So what do we want? Oi. Isso. Uhum. Exatamente. E o alfa é um multi-índice, né? Mm-hmm. So what we want is we want to show that f of C has measure 0. Okay, so we're going to have 3 steps. So the first step is to show that f of Ci has measure 0 for I sufficiently large. And then the second step is to show that f of Ci minus Ci minus 1 has measure 0 for all I. And the third step is to show that f of C minus C1 has measure 0. So knowing this, now we can write f of C as the union of finitely many sets of measure 0. OK, so if you combine these steps, then you can write f of C. This is contained in f of C minus C1, union f of C1 minus C2, union, etc., union f of C big N minus C n minus 1. And we know that all of these guys have measure 0. OK? OK. And you don't even have to take an infinite union, just a finite union. OK, so let's do the first step. Number 1. So we can assume that f of Ci, that U is contained in a cube. I assume that U is contained in a compact set, so it's contained in a cube of some side. So this is contained in a cube. I can write it like this. So it's contained in minus b over 2 b over 2 to the n. Okay, so a cube of size b. So cube of sides with length. I'm being a little careful here, and you'll see why. Okay? So by Taylor's theorem, or by Taylor's formula, we can write that f of x minus f of y. So we know that all the partial derivatives, so if I'm on Ci, I know that all the partial derivatives are 0 all the way up to order I. So that means that f of x minus f of y, when I look at this, again in L infinity norm, this is going to be less than or equal to some constant k times x minus y, L infinity, to the I plus 1. Okay? Because I have all the partial derivatives are 0 between 1 and I. Okay. So then, now what I do is I subdivide this cube into little cubes of lengths. So I subdivide this cube that I'm going to call R into cubes of sides B over R. So I have my cube, and I fix a number R, little r, and then I can divide it like this. So now the volume of each of these cubes is, of course, going to be b to the n over r to the n. But notice that when I apply f, then all the sides they are raised by the number I plus 1. So now basically I can write So basically my u is covered by I to the n cubes of sides b over r. And then when I apply f to them, so then f of u is covered by r to the n cubes of sides. Now my sides are b over r to the I plus 1. Okay? But what are the volumes of these cubes? So now the total volume here, so the total volume of these cubes is going to be r to the n times the side times to the m. And now this is, this is equal to k to the m. Oh, sorry, I forgot the k. There's a k here. Yeah, that enters there. So I have k to the m times b to the m times I plus 1. And then I have divided by r to the m I plus 1 minus n. Okay, so that's kind of the formula. And the point is, if I is sufficiently big, then this guy here goes to 0 as r goes to 0. Okay, so this goes to 0 as r goes to 0, provided that I is sufficiently big. So this, if I is bigger than n over m minus 1, I think that's the numerology. It doesn't really matter. It's a finite thing. It's not as I goes to infinity. It's like for a fixed I that's sufficiently big, this goes to 0. So that means that you can't actually cover f of u by a finite number of cubes whose volume is as small as you want. Sorry, what I want to say is it's u. It's not all of u. It's u intersected with ci. Because I have to be on ci to apply Taylor's inequality, Taylor's formula. Okay? Is this clear? Or are there any questions? So yeah, one more time, let me just say it again. So if you do this argument, if you just look at a cube and you subdivide it, and you don't know that the partial derivatives are 0 for a long time, then you're not going to gain very much by subdividing the cube and then applying f to every little cube. You're going to not really change very much by a big order. But if you know that you get that a lot of partial derivatives are 0, that's what allows you to kind of subdivide it. And you get an r to the n here, and then you get an r to the m, but that's raised to I plus 1. So that's what's going to allow you to kind of boost the m a lot. If you didn't have this, then you just have m minus n. And you only know that it goes to 0 if m is bigger than n. Otherwise, you're kind of stuck. Okay? So yeah, so this is kind of the key argument, actually. I would say this is kind of the most important part, the most important new part. And then the second and the third steps are not very hard. It's just kind of implying, they're not straightforward, but the induction actually happens here. But I would say that this is kind of the core part. Okay. So that's the first step. Now the second step now I want to look at Ci minus Ci plus 1. I don't know why I wrote Ci minus 1. Because Ci plus 1 is contained in Ci. Okay, so second step. So let's take a point P in Ci minus Ci plus 1. So if I'm in Ci minus Ci plus 1, then there exists a partial derivative g of f such that g of p is 0. There's an ith partial derivative such that gi of p is 0, and some partial derivative, dxi of p, is different from dx j of p is different from 0 for some j. Well, let me write it like this, for some j between 1 and n. Okay, so you can think g is d norm of df dx alpha for some multi-index alpha whose length, whose module is I. Okay? So, because I know that I'm in Ci, but I'm not in Ci plus 1. So not all of the I plus 1 derivatives are 0. Okay? So G has this property. And by, locally, if I take an open set near P, all of the points are going to satisfy this condition too, because this is an open condition. But not this condition. Okay, so now I can define a new function. I can let H be a function that goes from some U tilde in Rn, to Rn. So this U tilde is some open set containing P. And I'm going to define H to be x1 to xn. This is going to be H. This is going to be G of x1 through xn. And then x2, etc., xn. I'm going to suppose, without loss of generality, that this j equals 1. So I'm going to suppose j equals 1. Otherwise, you kind of flip this and you put the g in the position of j. Okay? Suppose, without loss of generality, you can always do a diffeomorphism to change the order, to suppose that the first it's the j equals 1, the first derivative that's non-zero. Okay. So now now you apply the inverse function theorem. So, by the inverse function theorem, you can basically, there exists an H tilde such that there exists an H tilde from U to Rn, or U tilde to Rn, such that H tilde, such that F composed with H tilde of Ci, F of Ci intersected with H tilde of U tilde is contained in 0 times In minus, no, sorry. I am mixing it up. So what I want to say is that sort of the G equals 0 part is the same as the image of a hyperplane. So this means that H tilde of Ci is contained in 0 times r to the n minus 1. That's what it is. Maybe Ci intersected with U tilde. There we go. Okay. Okay, so that's the inverse or the implicit function theorem, whichever one you like better. They're basically the same. So that means that if I do F composed with H inverse restricted to this subspace, this will be a function that goes from something in dimension n minus 1, or a subset here, some open set in here, into Rm. And the point is that f of ci minus ci minus 1, at least intersected with some neighborhood, is contained in this function, in the k, in k of the critical points of k. So this is kind of, this follows from this guy in the fact that this H tilde is a diffeomorphism, is a local diffeomorphism. So what I'm saying is, I can change this. I can change this function f to another function that is actually just a function from a hyperplane into Rm. Because I assume, because I'm only looking at the set of points which have one, which are going to 0 for one guy. Okay, so here I'm using this condition here. And I'm using this condition here to have the local diffeomorphism. Okay, but now k is really a function from where the domain has one dimension less. So now I can apply the induction hypothesis to say that this guy now is going to have measure 0. So by the induction hypothesis, f of ci minus ci plus 1 intersected with u has measure 0. And actually, I had to shrink this, so maybe this is u tilde. I had to shrink to apply the inverse function theorem. Okay? But it doesn't matter. If you can just prove that locally the intersection with any, if the intersection with a sufficiently small open neighborhood has measure 0, that's enough. Because you can cover your space with a countable number of them. Okay, so that's the second step. Any questions about this? And the third step is to go to C minus C1. And that's slightly more subtle, but it's almost the same argument. So let me rewrite what the third step says, because I already erased it. The third step says that f of C minus C1 has measure 0. And again, we're going to prove that f of C minus C1 intersected with a sufficiently small open set has measure 0. Sim. This is the inverse function theorem or the implicit function theorem, if you want, because what is Ci intersected with u tilde? So Ci, if u tilde is a small neighborhood of P. So if I'm in Ci, if and only if g of P is 0. Because if I'm sufficiently small, this condition always holds. This is an open condition. So in u tilde, this always holds. So I'm in Ci if and only if g of P is 0. Okay? So if I have this condition, then by the implicit function theorem, I can write, what's the 0 of this as the graph of some function. That's the implicit function theorem. But another way to see that is that there is a local diffeomorphism that takes this guy to 0 times something of dimension n minus 1. Okay? So, yeah. So under this diffeomorphism, I am on G, or I'm on Ci, if and only if the first coordinate is 0. Okay? So, it's like writing H like this. Maybe I could have written it slightly nicer, but okay. Yeah. yeah, I guess the point is that this h tilde is the inverse, is the local inverse of h. So by the inverse function theorem, h tilde, which is h inverse, is this. And there we go. Yeah, sorry, I kind of copied half of my notes, and then the other half I kind of did it in front of you, and then it was a little choppy. Okay, so the rest is the rest. Okay, so number 3 is very similar, but it's a little different, because if I'm on C, but I'm not on C1, I don't know that sort of the F is equal to 0 there. I want to basically look at all the critical points on C, and that could be a funnier set. So I have to be a little bit more careful. So the proof is the following. So take a point P, which is in C minus C1. So then, without loss of generality, we can suppose it's the first one. So we can suppose that it is. So if I'm not in C1, then one of the derivatives is not 0. So then d, I can suppose that it's d f1 d x1, which is non-zero. And then I can write h of x1 through xn, which is f1 of x1 through xn, then x2, and then xn. Okay, so far it looks very similar to step 2, but you'll see it's a little bit harder. So now, by the inverse function theorem, basically I can, there exists, basically H was going to be a local diffeomorphism. H is a local diffeomorphism. And I can write F tilde as F composed with H inverse locally. So in some kind of U tilde contained in Rn into Rn. And that's because of how I defined H, I'm going to have the property that F tilde of x1 through xn is equal to x1 and then some other function, which I'm going to call g of x1 through xn, where g is a function from some set from U tilde into Rn, M, Rm minus 1. Yeah, that's right. Okay, so over there it was easy because if I restrict it to my critical set, I actually had everything taken to x1 equals 0. So I kind of already could do the induction right away. But here it's not so obvious, because I don't know that when I restrict this to the image of the critical point set, I'm going to just go to one slice to just x1 equals 0. That's not true in general. Okay, so that's why we need one more step for this case. So what is it? So first notice that that the critical point set of F, if I intersect it with U tilde, and I look at H of that, if I look at the critical, if I look at the points that are critical for F tilde, because the H is a local diffeomorphism, they get taken to the critical points of F by H. So if I look at H of this, that's just going to be the critical points of F in this U. Okay, so H is a local diffeomorphism, so H is taking U to u tilde. Okay? And f tilde is only takes values in u tilde. That's why I'm not taking the intersection with u tilde. Okay, but H is a local diffeomorphism, so it will take the critical points of f to the critical points of f tilde and vice versa. Okay? So now I can just look at this f tilde. Okay, so now we look at f tilde, and let's let gx be a function from, well, let's just write it like this. Wherever it's defined, gx of y will be equal to g of xy. So x is a point in R, and y is a point in Rn minus 1. Provided that xy is in u tilde, in the domain of G. I'm just writing this so that we can see what df tilde is. So df tilde is going to be it's going to be 1 here. It's going to be 0 here. It's going to be something here. And it's going to be d of gx at the point y. So now you see that df tilde is that xy is a critical point of f tilde if and only if y is a critical point of dgx. So kind of this is the key thing. xy is a critical point of f tilde if and only if y is a critical point of gx. Yeah, see, gx basically goes from some subset of, I'm just going to write it like this, Rn minus 1 to Rm minus 1. But it's some subset of Rn minus 1. Some sufficiently small open subset, if you want. Okay? And here, and one more thing they can write is that, now if you apply the value of the function, if you apply f tilde to f tilde of this, so the set of critical values of f tilde is equal to x times the critical value of this guy. This is a consequence. But union over all x. Okay. This is almost tautological, but maybe it's an exercise of definitions and writing down things. But it's not hard to convince yourself of this fact. So now, by the induction hypothesis, gx, so the set of critical values of gx has measure 0. In Rm minus 1. Okay, because gx is a function that goes from Rn minus 1 to Rm minus 1. So the domain has dimension 1 less. And I said that the induction is on the dimension of the domain. Okay, so by the induction hypothesis, this has measure 0. So now we have to apply a theorem called the Fubini theorem in measure theory. And I'm not going to prove it. You can just prove it, the Fubini theorem for measure 0 if you want. It basically says the following thing. So if I have some set in Rm such that each slice has measure 0 in Rm minus 1, then the whole thing has measure 0. So this is the Fubini theorem for measure 0. Let me just write this lemma, and I'm not going to prove the lemma. But the lemma is the Fubini theorem for measure 0. It says the following thing. So if I have a set X in Rm such that when you project X along any, so let's say, yeah, so Prx of X has measure 0 for every X in, for every X equals to, well, I just want to project it in the, so let's say for every 0, 0x in Rm. So if I project, actually I'm projecting on the first coordinate, along the first coordinate during Rm, has measure 0 in Rm minus 1 for every point like that. Then X itself has measure 0. I mean, that's basically, if you're trying to, if you're looking at the volume of some set, just writing this in terms of measure theory, like, of 1, this is, and you know that there's one direction in which every slice has measure 0, then this has measure 0. Okay, so if you want, you can look at this. You can look at this theorem in a measure theory book, or I don't know, in anywhere where you see this proof of Sartre's theorem. Maybe they prove this too. But I don't want to say any more words. Or if you haven't seen this before, it's actually a very nice exercise in just volumes of cubes and this kind of stuff that we've done. And of course, now if we know this, then this guy is a union over X of all these, of all these slices. So then by this Fubini theorem, then the critical value set of F tilde has measure 0. And that finishes the induction. And that's the end of Sartre's theorem. All right. So we'll stop here for today.